his via his LLC. In November 2006, he retired from full-time employment with U.S. NRC, Nuclear Regulatory Commission, where he worked for a total of 27 years in various capacities. As a manager for much of his career, Mr. Essig, my friend Tom, provided direction and leadership to health physics, emergency preparedness, and nuclear power plant and radioactive material licensing, waste management, and environmental protection programs, as well as incident response activities. Earlier in his NRC career, Mr. Tom served as a reactor licensing reviewer and reactor health physics inspector on separate occasions. Tom was also employed by the U.S. Department of Energy's Pacific Northwest National Laboratory on 2 separate occasions, totaling nearly 16 years. While there, Tom managed research and development programs in the areas of health physics and emergency preparedness for various governmental and commercial clients. Initially, he was responsible for environmental surveillance and occupational radiation protection programs at the Hanford site. Tom has a BS degree in applied engineering physics from Michigan Technical University and an MS degree in environmental engineering from Washington State University with a special emphasis on radiation protection. The last thing, the big ticket item, he is a certified health physicist. That's a big ticket. So I feel like if you are concerned about environmental impacts of the radiation, the impacts of nuclear power on the environment, he's the guy to go to. So please welcome my friend Tom Essig.
Okay, Tom, it's all yours.
Okay, thank you. Let me do a share screen here.
Yep.
And okay. And there we are. Okay. Everybody see the screen okay?
Yep, very nice.
That is a picture of 3 Mile Island nuclear power plant, just near Harrisburg, Pennsylvania. And that, of course, in March of 28th of 1979, there was a little event there that was the worst nuclear power plant issue in the US. And then that was followed by 2 other accidents that we'll be talking about. But anyway, that is the island itself. I mean, it's actually an island in the Susquehanna River. And I was there on day 2 following the accident. My employer, the NRC, sent myself and several others to support the regional office that who's had the lead for oversight of the plant. And so we were there, well, I was there a total of about 4 months, having a lot of challenges. Okay, so let's go, if I can hit, whoops, now why isn't it? I am trying to hit page down. Oh, there we go. Okay, and this is where it started in under Stagg Field in squash court at the University of Chicago. And this, what's displayed here is a depiction of the what's called Chicago Pile 1 or CP1. And if I can kind of point to a couple things here, these are graphite blocks, and that served as the moderator to keep the chain reaction from getting out of control. And we'll get into a little bit more of that later. But this was an artist depiction of, and Enrico Fermi from the Italian physicist was there, and he was kind of running the show. And this that is sticking out here was one of the control rods that helped keep the reaction that was going on inside of this pile under control. But that's where it all started, the first chain reaction. And talking about chain reaction, this is what happens when we have this small atomic particle called a neutron. It interacts with the uranium-235 nucleus, which is called fissile, meaning that it will absorb the neutron, it becomes unstable, and it'll split, as the big blue arrow there shows. So it splits into two what are called fission products, and it releases a lot of energy, as is shown here. But it also releases several of these neutrons. So one comes in, the uranium atom splits, and then two to three neutrons then go off and they interact with other uranium atoms. And so it keeps the chain reaction going. When the number of neutrons is balanced, we have a sustainable reaction. When it's out of balance and we don't have any controls, then we have a nuclear weapon. So, and there's obviously a distinction between the two. When you want the chain reaction out of control, like we did at Hiroshima and Nagasaki, Japan, well, then you don't have any moderator, and you just let the weapon in less than a second do its horrible job that it was designed to do. Okay, so here we have what we want to introduce you to a couple of concepts here. We have the fuel that's depicted here, and it emits the neutron, and then there's a term here called a neutron moderator. The moderator is necessary, and the water that's depicted here actually acts as a neutron moderator. So in order for another U-235 atom to capture a neutron in fission, that neutron has to be slowed down so that it can be caught, so to speak, by the nucleus. And so that's the function of the moderator. And so it will then, this is uranium trioxide, the fuel rod. They're little pellets. I think maybe I have a picture of them coming up later. The other essential component here is heat transfer. And so that's what this water that comes in, it serves two purposes. It cools, it removes heat from the reactor, and it also serves as a moderator. And so basically what this does is it generates steam that goes to a turbine generator to produce electricity. So we'll have a little bit more about that in a bit. But these are the three essential agreements to having a nuclear power plant operate. So here we have this is depicted of the core of the reactor, so to speak. These red things here are fuel rods. And then coming down from the top are these movable control rods. So the control rods absorb neutrons. They keep the neutrons from getting out of hand. And if they did get out of hand, we'd have a detonation, as I mentioned earlier, as a nuclear weapon. So anyway, these control rods are used to keep the number of neutrons at about the right point to keep the chain reaction going. And so we have water coming in here, flows up through the core, and then hotter water comes out. And so a fuel assembly is depicted here. So we have these fuel rods that are in this assembly, and they're little pellets inside of these zirconium tubes that make up this what's called a grid here. And so if we go down to the next one, when this uranium atom splits, this neutron comes in, it generates what are called fission products. And so there are three categories that we normally think of in terms of fission products. We have what are called noble gases. And if you remember back to your high school chemistry, noble gases were those that don't interact with anything, like helium, neon, xenon, krypton. So there are some noble gases that are produced, and but these noble gases are of interest because they're radioactive forms of the common noble gases. So then we have halogens also that are produced in these fragments here, and this is radioactive iodine. And then we have radioactive materials in particulate form, cesium, radioactive cesium, rubidium, ruthenium, and numerous others. Okay, so then to make sure that everything goes like we want it to, we have these, we need safety systems. And of course, there are multiple safety systems. It's we've referred to often as an onion. So you peel a layer of the onion, and underneath is another safety system, and underneath that is another safety system. So it's defense in depth is what it's normally called. And so we need multiple sources of water. And there's a rule number 1, don't turn off the water, because that's what happened at 3 Mile Island. And then rule number 2, simply see rule number 1. So even when the control rods are inserted and no fission is taking place, the fission products produce decay heat that must be removed. So that's why we need to keep the water, even if the plant is shut down, we need to keep water circulating through the core. And then we offload the spent fuel from the reactor, and we put it in what's called a spent fuel pool, and that continues to generate from the fission product decay, generates heat. And ultimately, that gets to the point where we can actually remove them from the spent fuel pool. Okay, so a couple different kinds of reactors that we have. 2 in the US, we have what we call a boiling water reactor. So we have here the reactor itself, the control rods. In this case, they come up from the bottom. That's the way this reactor was designed. The General Electric company is the main designer of this type of reactor. There are 31 of these in the United States that are operating presently. And so this generates steam. You're actually just boiling water, and then the steam goes over to the turbine, turns the turbine turns the generator that produces electricity that goes into the grid. And then this steam, when it goes through a condenser and comes back as water then, and we end up just kind of repeating the cycle. So it just kind of flows through the, I'm sorry, I jumped ahead inadvertently. The next one is the pressurized water reactor. It operates a little differently in that the steam that's produced doesn't come from the reactor itself directly. It comes from what's called a steam generator. So we have this pressurizer on here, so it doesn't allow this water that's circulating to ever boil. So it's at a temperature of about between 500 and 600 degrees Fahrenheit as it's circulating through here, but it's kept under pressure so it doesn't boil. But then it flows through the steam generator, and then the water that comes up through the steam generator turns to steam, goes over to the turbine, much like the other boiling water reactor that I showed earlier, and then it goes through a condenser and so on, and then the power goes off the grid. This is, there are 62 of these operating in the United States. So 62 and 31 is total 93 nuclear power plants that are currently operating. This is down a little bit from 104 that just a few years back that had been operating. Those plants, the owner just decided not to renew their operating license, and so the plant shut down. And then we go down to the next slide where we talk about barriers. These are important because they are what keep the radioactive material in the fuel rods, where in these little pellets here that are, it's uranium oxide that has been subjected to quite a bit of pressure. And whoops, I don't know, I didn't want to do that, sorry. Subject to quite a bit of pressure, and they're sintered. And so they're probably about half inch long or so, and a little bit less than that in diameter. There's a whole bunch of them then that go inside this fuel rod, which has cladding on it, zircaloy cladding. And then, so then the reactor coolant system is another barrier, and then the containment vessel, that's outlined here. Those are all served to keep the radioactive material from being released to the environment. So we have various systems that protect the fuel cladding, protect the reactor coolant system, and protect containment. So that's basically the idea, is to prevent an accident from happening. If it does, I mean, to keep it under control, if one does happen, we make sure that we have very rigid defense in depth on each of these safety systems. And even if we lost 2 of them, and we still have our containment that is designed to be basically a large pressure vessel that will contain the radioactive material. So this first barrier, as I mentioned, you can see the size of the fuel pellet, kind of what they look like. This just shows a fuel bundle, which is a bunch of fuel rods that are in these tubes. Second barrier, the coolant system. It's basically all of there's a lot of associated plumbing, as it's referred to here, that injects the coolant, and then it removes the heat from the nuclear power plant. And then the third one, the containment. It's just a large vessel that surrounds the reactor. This here is depicted as the pressurized water reactor, which there are 62 in the operating units in the US. And then we have the spent fuel pool. And you see here, well, there's lighting, but if you turn the lights off, the spent fuel you'd see a blue glow, which is kind of interesting. I've seen that when the fuel is freshly discharged and put in the spent fuel pool. There's what's called Cherenkov radiation that was named after a Russian, and it means that the radiation is actually exceeding the speed of light, and so it ends up with this blue glow, and so this is under 30 plus feet of water, and the water acts as a very good shield. And so you can actually walk around the perimeter of the spent fuel pool. Now, what happens when the fuel is removed from the pool? We don't have a infinite capacity to keep spent fuel in the water pool. So after it's been there about 4 or 5 years, the decay heat has reduced enough to where it can be offloaded and stored in one of these spent fuel storage canisters that are depicted here. And unfortunately, this is, we don't have spent fuel reprocessing in the United States. During the Carter administration, they decided that the risk of reprocessing spent fuel to recover the plutonium that's produced during the irradiation process was too great, because we needed to safeguard the plutonium and keep terrorists from stealing it and making a nuclear weapon. So they decided the risk was too great, and so we're not going to process or reprocess spent fuel. The decision was made, and so now the only choice we have is to store the spent fuel in the assemblies that have the radioactive material. And we have this actually has a long name. It's called the Independent Spent Fuel Storage Installation, this array here, or ISFSI as it's called for short. And so every nuclear power plant now has one of these spent fuel storage installations on site, because they have no other place to be able to store it, which is kind of the Achilles heel of nuclear power, which is why it hasn't grown, at least in my opinion, why it hasn't grown faster than it has. There are 2 issues. One is the handling of the or dealing with the radioactive waste, high-level waste. And if we had fewer processing, we could have a more, we'd still have high-level waste, but it will be a more manageable problem. And then the other is the sheer economics of a nuclear power plant. I mean, we're talking about upwards of $5 billion or more to build a plant. And because of the cost of all the safety systems and that sort of thing, they've just become very, very costly to operate. And the belief always was that, well, if we make them bigger, the cost per kilowatt generated, it will go down. And that's true, but the cost of the plant has been going up. So the economics and the what to do with the spent fuel are two of the big problems that need to be solved. And so hopefully the day will come. And these canisters have a design life of about, their concrete shielding with a steel liner, they have a design life of about 300 years. So sometime between now and 300 years from now, we're going to have to solve this problem because these containers will be at their design life, near the end of their design life. This just shows how we transport spent fuel over land. This is an approved, called a Type B container. And these things undergo very rigorous testing. I've seen video clips where this container that's on this truck, it's parked on a railroad track. They have a locomotive that is zooming toward it. It crashes into the spent fuel cask, and no damage is done to the spent fuel cask. I mean, it literally goes airborne, and but it comes down and it's maybe dented here and there, but no damage to the contents. Okay, here was to be the future of high-level waste, Yucca Mountain in Nevada. This is just one of the tunnels, and this is a ventilation shaft that's up here. I've been to that site. It's very well constructed. You tunnel right into this mountain, Yucca Mountain, and the citizens of Nevada were violently opposed to it. And so the Nuclear Waste Policy Act of 1985, basically we had studied a whole bunch of potential candidate sites for high-level waste disposal, and Yucca Mountain was selected. And so then by law, there's supposed to be this site in operation in Nevada, but there's been enough obstructions, lawsuits, and what have you that have prevented it from receiving spent fuel. So it sits there basically unused, and which is really kind of unfortunate, but that's the way we are. And there were two designs. One was going to be to seal it permanently after it reaches capacity. The other is to not seal it after reach capacity, thinking that it would take a while to fill it, and then we could remove the spent fuel if we had reprocessing it someday way in the future. So there were two options that were envisioned, but both are kind of moot points now because it sits there basically unused. Okay, so let's talk about what goes wrong. 3 Mile Island Unit 2, and there were two in the very first slide, a picture of 3 Mile Island. We had a mechanical failure and an operator error. And in this case, the contained structure worked. There were still some noble gases that I mentioned earlier that were released. In fact, my workstation was, along with other people, we were about a half mile from the plant as the crow flies, and we were on the one bank of the river, just looking down at the plant on day 2. And we had our instrument on always, and our Geiger counter in the office where we were, in the trailer where we were working. And when the wind was coming our direction, you'd hear the click rate on the Geiger counter would be increasing, and we knew, okay, we're being exposed to noble gases. And so it was a low level but measurable amount of radioactive material that was being released to the environment. And but the public dose limit was not exceeded by any at any location around the site, and so there was a lot of concern that was expressed, and a number of what if situations were concocted, and but in the actual accident itself, I mean, clearly a lot of damage to the plant, so it could never be operated again. But the impact on the environment was rather minimal because it was within the public dose limit that's specified in the in NRC regulations. Okay, then a few years later, Chernobyl came along, Unit 4 of Chernobyl, and you can see in this picture, the Russians at the time didn't believe in containment structures like we have in the US, where the building that I mentioned earlier that is designed to contain the radioactive material, it's designed to operate at a certain pressure. But the Russians didn't believe that in that technology, too costly, and so they ended up, they were doing some testing, got away from them, and led to a core melt and a graphite, because they used graphite instead of water for their moderator, and they actually had a graphite fire, and so that's what ended up being. So we have a big empty spot there where the building was. So this just gives a little narrative on what happened, and then there was a lot of radioactive material released because it was just basically totally open to the air, and on that roof of that building that was there were individuals, and I think there were 32 of them that ended up being so exposed that they ended up dying from the radiation exposure. They were called liquidators, and these were people that were directed to, with a fire hose, to any way they could to get water on this down into this cavity where the hole had burned through the roof. And so that was their mission. They were standing up there with fire hoses and the huge amount of radioactive material being released. And as a result, they had 32 deaths. Well, come back to 3 Mile Island, there were 0 deaths from 3 Mile Island. So we must have done something right, or the Russians did something very wrong, if you want to look at it that way. So, it talks about the graphite blocks used as the moderator. They caught fire as well. So flawed reactor design. There were 2 plant workers that died due to the explosion on the night of the accident, and then another 28 people a few weeks as a result of what they were trying to do to keep water flowing in the plant. And there were 350,000 people evacuated, and there was 5,000 thyroid cancers that were produced because they didn't use what was called, this was, I believe, in Belarus. They didn't use what's called a thyroid blocking agent, or potassium iodide, that we now use, and they had it at the time, but didn't. The government of Belarus didn't believe in using it because they were still part of this. Their government was just still tied to the Soviet way of thinking, and so they didn't offer that to didn't have it available to offer to their population. So there are a large number of thyroid cancers that resulted. And then most recently, we had the Fukushima Daiichi plant in Japan, and it ended up in a here's where it's located right here. And these were all the nuclear power plants in Japan, and then those in South Korea are depicted over here. So Japan has quite a few nuclear power plants because they don't have any, I'm sorry, I did it again. They don't have any natural resources, or very little, so they're dependent quite a bit for their power generation on nuclear power. And so this plant, we'll get into a little bit more of what happened there, but it was a 6-unit boiling water reactor the reactors themselves are along here, or actually back here, I'm sorry. This is the turbine generator building, but back here are the 6 nuclear power plants or reactors and the reactors there were GE boiling water reactor model, boiling water BWR3, which was in GE's system. The BWR1 was the first one that they offered, and then current, I think the last offering they had was of this type was a BWR6, and so this was about halfway through the evolution of the GE models, and these are just some of the aspects of the containment. The primary containment is here. This shell, the torus would provide cooling water, emergency cooling water. And then the condenser shown here, the steam line that comes over, goes to the turbine, condenses, and so on. Kind of like what we walked through before. And so what happened here was they had a very large earthquake, which shut down the reactors. The problem is they lost offsite power. And in the situation here, they had their spent fuel pool, the diesel generators that provide emergency backup power were located at a level in the plant that they thought was well above any possible ever flooding that could occur in the future. Had they located the diesel generators just a little bit higher, another level in the plant, the tsunami, the big wave that came in, would have not flooded the diesel generators, and the accident probably would have never happened, or at least it would have been much less severe. But when they took out the diesel generators, they lost offsite power, and they had no option available to them, but they sustained rather significant core damage. And so the lesson learned from that is do a thorough evaluation of seeing what could happen. And they thought they had bounded it adequately, but they didn't anticipate the tsunami of that magnitude. And then they had to evacuate quite a few individuals. And then we'll jump to future reactors. I think there will be a future. And there's a company called NuScale that was gotten its start down at Oregon State University with the nuclear engineering program at Oregon State. And this is called a small modular reactor. And in this case, there are up to 12 separate reactors, and they're ganged together. They're operated by a single control room, and each power module has its own containment vessel, and shows a spent fuel pool over here. And then the reactor pool for each of the reactors here, the biological shield, that's the concrete shield that keeps us from being exposed. And this design is considered to be not only by the company, but by others that have reviewed the design to be as inherently safe as you can get, meaning that if something happened and I couldn't get operator attention, the reactor will be, the core will not melt. And so I have what's called here natural circulation cooling. So even if I lost the ability to pump water through it, this natural circulation will keep the fuel adequately cooled. And so I think let me see. Oh, yes. We have our end slide here is Godzilla. That isn't my creation. The gentleman that created these slides that I'm using, that was his idea of the end question mark. So anyway, I will, I'll leave the slides here in case there are any questions, and then I can just flip back to any of the slides that we need to. So I'll just kind of leave them there and open it up for questions if you have any.
Please raise your hand if you have a question.
And I realized that it was kind of technical. I don't know how else to present the material. It's a very technical material, and but hopefully you got something out of it.
Yeah,
And,
very impressive. Thank you very much. I learned something, definitely.
Gunda, I have a question.
Go ahead.
Okay. What is your opinion of the, the possibility of a disaster in Chernobyl in Ukraine?
That I kind of figured this question would be coming. It's a natural question to ask. There are Ukraine has several operating nuclear power plants, and I don't know if I could speculate what the Russians are going to try to do. I don't know why they would want to. I think if they did anything to the Ukraine, to the Chernobyl plant, it has a large containment structure around it that keeps the radioactive material inside. Now, I don't know if they would want to attempt to breach that structure, blow a hole in it or something, just to frighten the population, to make sure that they evacuated from the area. I don't know what motivation they would have to do anything to the Chernobyl plant itself. They're possibly, I think the Russians have tried to seize operation of the existing operating nuclear power plants in the Ukraine. How that would play out and what their intent is there, I don't know. But yeah, that's one of the things that unfortunately we have to stay tuned and see what evolves as the Russians continue to spread themselves across the Ukraine and causing havoc within the country as best they can. But I don't know if I can really give you a good answer to the question. It's not. They could stop short of really doing anything, just threatening to do something and then stopping short of actually doing anything with the operating plants, or they could attempt to breach the containment at the Chernobyl plant, just so that they could say that or threaten to do it. I just don't. It's kind of difficult to speculate because Putin is he's doing some things that I think most people believe that nobody in their right mind would be doing, but he's doing them nonetheless. And so with that mentality, it's kind of hard to predict what it is that he may instruct his military to do as that war continues to go on.
Thomas, thank
So,
you very much. Yeah. Any questions? Any other questions?
Yeah, hi, this is
I just want Tom to comment about the green effect of a nuclear plant as opposed to other sources of electricity production. I just a short comment. Do you think
Sure.
nuclear power produces less
Sure.
of a carbon footprint?
it doesn't produce any greenhouse gases. Is the I mean, yes, there are other things to concern ourselves with. As I mentioned, there are fission products that are produced that we have to contain, but there are no greenhouse gases that are produced by nuclear power plants, and so that's it's truly considered to be, among others, the solar and wind and so on, to be green, a source of green power, and the unfortunate thing is the petroleum companies would, particularly when talking about natural gas, they always advertise it as clean. Well, clean in what sense? You burn natural gas and you're still producing carbon dioxide, which is a greenhouse gas. So I would say that there's a little more than a little bit of false advertising on the part of the natural gas producers that want you to burn natural gas as a so-called clean fuel. I mean, yes, it's relatively clean. It's probably cleaner than well, certainly cleaner than coal, and probably cleaner than fuel oil that we used to use a number of years ago. But I don't think it's to call it green, natural gas as being a green source of electricity. I would say no, because of the carbon dioxide that's produced. I mean, you have hydrocarbons that the gas consists of, and you combine it with oxygen and you get heat and carbon dioxide produced. So it's not a green source of power. Natural gas is not.
I think Guy had a question.
Sorry, yes, Guy, go ahead.
Yeah, that's right. Hi, Tom. I actually grew up in the Tri-Cities, and I know a lot of people who work out in the area, and I've got a million questions, but well, this one I've got kind of more towards the green thing.
Don't hear you, Guy. You lost
Can't
it.
hear you.
Guy, you lost your audio. Guy,
Oh,
no, we lost him.
Or just, and then showing you on your presentation, just showing the meltdowns. Nuclear energy has just gotten such a bad name or bad rap through the years, and so many people, like in Yucca Mountain, and so you couldn't do any encapsulation in Yucca Mountain. So it just seems that there's a misunderstanding from the general public. So my question was kind of along with the green. I mean, if with new technologies and stuff like NuScale, don't you think that we should be able to, because we haven't built nuclear facilities in a long time. They're very old, and
right.
And they're not allowed to do any. And like you said, the cost of doing like a new FFTF would be $5 billion. So it just, I was just wondering, I was hopeful that there'd be some new designs and some new build to generate that clean energy in a better, in a cost-effective way now with gas and all the conflict going on in the world. I mean, is there any plans, I guess I should say, for the government to do that, or releasing a lot more to like private companies, because there really aren't any private companies that manage nuclear power?
Yeah, to answer your question is yes, I think I'm optimistic regarding the future of nuclear power, and the future is going to be, I believe, in the form of these NuScale, the plant that they offer, the small modular reactor. GE and Hitachi has another design that they are offering, and I believe there's a third company that are maybe even more that are offering some of these newer designs that are, and I believe that the NuScale design is, they advertise it as inherently safe. And I really believe that it's about as safe as you can, safe as you can get. Now, does that mean there's zero risk? Of course not. But the risk factor has been reduced significantly. And as I mentioned earlier, it can have an event that occurs, they lose power. they don't even need to worry about pumps that have to come on to move water because it'll circulate through the core through natural circulation. And so I
Right.
think if there is a future, it's going to be certainly with concepts like the new scale design, and
Right.
it is moving right along.
But the regulations from the government, like to protect from terrorists stealing, the spent fuels and things like
Oh,
that.
I know.
I mean, the regulations for private companies almost would have to be, in collaboration, because I can't imagine just having someplace in the, downtown Tacoma or something that wouldn't be able to be so secure,
Yeah.
it would be difficult, but.
That one of the problems that we get into was because was spent fuel that used to be considered as self-protecting, meaning that after the fuel comes out of a nuclear power plant, it's so radioactive that by self-protecting, meaning that nobody in their right mind would attempt to steal a spent fuel assembly. But what happened with, as time has evolved, some of these terrorist organizations have proven that for their cause, they would send somebody in to grab a source, would hand it off to somebody else and hand it off to somebody else. There might be a whole bunch of people that died, but in their way of thinking, they would have accomplished that for the right reasons. And so what we used to consider to be self-protecting only meant that nobody in their right mind would attempt that, but we have a lot of people that aren't in their right mind and that will attempt it. And so that's why I think a lot of the safeguards that we currently have will probably stay in place for some time until we can develop a system that's basically, if we process spent fuel, which I personally think is a good idea, because you can recover the plutonium from the spent fuel, and the plutonium itself is usable as reactor fuel. So you have it's basically a built-in recycle mode. And then the residual that you have left, you still have high-level waste, but it's a much smaller problem to deal with. And so I don't know the economics of it. That's where.
Hi, Thomas. I think we are
Yeah.
way over time right now. So if
I'm
you guys
sorry.
want to continue talking to
Yeah.
each other, it's fine. But our meeting is over.
Okay.
If you want to stick around and go ahead and ask more questions to Thomas, fascinating topic. I really appreciate your presentation.
Okay.
Really great
You're
stuff.
most welcome. My pleasure.
Very
Thank
nice.
you,
Thank
Mike,
you so
for
much
having
for
me.
coming, and Dennis to make it
Sure.
happen. Wonderful.
I really want to thank you, Tom.
Oh, you're welcome.